Hello, class. Today is the first day of properties of solutions. We're going to cover some solutions vocabulary, factors affecting solubility, chromatography, Henry's law, concentration calculations, and of course some example problems. This goes well with Quest Solutions Basics, and a lot of this should be a review from honors. Okay. So just some of the general terms about solutions. A lot of this you should have seen in honors. We should know what a solution is by now. It's the homogeneous mixture of two or more substances. The solute is the thing that is in the smallest amount. It dissolves in the solvent. The solvent does the dissolving. Solubility is describing the amount of a substance that can be dissolved in a given quantity of solvent. It's often expressed in grams of solute per 100 grams of solvent. When you see solubility curves on a graph, that's what that is referring to. If something is miscible, it means that two liquids that dissolve in each other in all proportions. If something's immiscible, they do not dissolve. We also have molar solubility, which is the number of moles that dissolve per liter of solution. Some of the factors that affect solubility, we have to think back to kinetics and our collision theory, right? If we increase the temperature, it increases the likelihood of those things colliding. Specifically, we're talking about the collision of the particles, the solute particles, and the solvent particles. They have to collide with enough energy and with the right orientation in order to overcome the solvent-solvent interactions and the solute-solute interactions, so that we can then get solute and solvent interactions. So stirring also helps that and increases the likelihood of collision, and also expanding the surface area of the solute. There's more surface area, it's more likely to react. And again, the idea is that we have solvent-solvent interactions. We have solute-solute interactions, and what we want is solute-solvent interactions. So we have to overcome these two in order for the third to happen. Okay. So if we are going to talk about solutions, we do want to connect intermolecular forces to these properties. We know that substances that are composed of nonpolar molecules typically experience London dispersion, and therefore they are not as attractive to each other, and so they typically are low boiling liquids, or they exist as gases. Whereas with polar molecules, we generally have higher boiling points because you have dipole-dipole forces, hydrogen bonding, sometimes dipole-induced dipole, things of that nature. Those things are typically solid at room temperature. And the reason this matters is because when we start looking at solutions, we always know oil and water don't mix, but that's because of the polarity of those things. You've got nonpolar and polar things trying to mix together. They don't mix because they experience different intermolecular forces. So our general rule is that like dissolves like. We know that things that are polar or ionic will dissolve in things that are also polar. We know that nonpolar things will dissolve in nonpolar substances. And again, it has to do with the type of forces, intermolecular forces they experience when they come in contact with each other. So another good visual here, you've got water experiencing hydrogen bonding. We also have methanol experiencing hydrogen bonding. And so since they are both polar molecules, methanol can be dissolved in water, and you'll see some of these methanol particles in a network here with the water molecules. You'll also notice the water molecules change their orientation depending on who they're interacting with. Right? So key thing for dissolving, and this goes back to kinetics, we have to have the right orientation and the right amount of energy. When we're looking at solubility curves, this is a solubility curve. Notice it's in grams of solute. It's grams of solute per 100 grams of solvent. In this case, the solvent is water. You'll notice that as we increase the temperature, generally our solutes dissolve more readily. You'll notice that solutes where there's only two particles. Here we've got potassium and bromine. Those are two particles. They split into two ions. Those things generally increase, whereas things like sodium sulfate, you get three or more particles when they dissolve into their ions. And those tend to dissolve less as temperature goes on. We also have gases. The solubility of gases tends to decrease with temperature. So where solids increases with temperature, gases decrease with temperature. That makes sense if we think about soda. If you have a cold soda, there's still plenty of bubbles in there, but if we let that soda sit out, as it warms up, it starts to get flat because all of the bubbles, the carbon dioxide bubbles, are escaping. So as the temperature goes up, they are less soluble and therefore they bubble out. So here's our task. We must decide whether liquid hexane or liquid methanol is more appropriate solvent for grease and potassium iodide. So we need to identify the polarity of those things. We know that grease is a hydrocarbon, so it is nonpolar, whereas potassium iodide is ionic, therefore it will dissolve best in polar substances. So if we want our grease to dissolve, we want to use liquid hexane because it is nonpolar, right? Have to have the same polarity. Methanol would do a good job of dissolving Ki because it is ionic. Remember, the like dissolves like rule. Okay. While we're on the topic of polarity, this doesn't typically fall in this unit, but it is good to talk about chromatography, which is a separation technique. This did show up, I believe, in the 2017 exam as one of the FRQ questions. They talked about thin layer chromatography, which threw a lot of people for a loop. And all it is an application of solutions and the like dissolves like rule. This is typically a technique that is used to separate compounds based on their polarity. So you have a solvent, you have solutes that you're trying to separate from each other. You pour the solvent through them and they will separate based on polarity. If they're polar, obviously they're going to be attracted to either the polar stationary phase, or if the stationary phase is nonpolar, then they won't be attracted to the stationary phase and they'll be attracted to the solvent. So say we have a polar solvent, it will attract all the polar things and drag them down the column or across the paper, the stationary phase, if you will, and those things will come off first. You get a separation based on polarity, whereas things that are less polar or nonpolar will be left behind. So in column chromatography, you tend to see that you've got a stationary phase, which is typically sand. It's nonpolar. And then you've got a polar solvent, and that polar solvent mixes with your mixture, and they start to separate out based on polarity, and you get distinct regions or bands where those things separate out. And again, it's all based on polarity. If something is more attracted to the solvent, it will go further down the column. If it's less attracted to the solvent, it will stay at the top. Same deal with thin layer chromatography down here, sometimes referred to as TLC. Depends on what kind of solvent you're using, but the retention of the pigments will vary based off of what kind of substances are dissolving in your solvent. So the key here, if you see a problem like this, look at the solvent to figure out if it's polar or nonpolar, and then use that information to judge the polarity of the components that are separating. Things that would be further away are likely to be polar because they separate last if they're attracted to a polar solvent. Henry's law. So Henry's law states that the amount of gas dissolved in a solution is directly proportional to the pressure of the gas above a solution. The conditions we need here, we need dilute solutions of gases that don't dissociate or react with the solvent. The equation for Henry's law is the concentration C of your dissolved gas is equal to some constant K times the partial pressure of the gaseous solute above the solution. Okay. As we increase that pressure, obviously the gas stays dissolved. If we decrease the pressure, less gas will remain dissolved. So we're going to talk about soda here, and we're going to look at this problem. It says a certain soft drink is bottled so that at 25 degrees, the pressure of an unopened bottle is 5 atmospheres over the liquid. Assuming that the partial pressure of CO2 in the atmosphere is 4.0 times 10 to the negative 4th atmospheres, calculate the equilibrium concentrations of CO2 in the soda both before and after the bottle is opened. Henry's law constant for CO2 in aqueous solution is 0.031 moles over liters times atmosphere at 25 degrees Celsius. Okay, so again, we need the equation C equals K times P of CO2. All right. So for the unopened bottle, they want before and after, right? Unopened, I'm going to need my constant 0.031 moles over liter atmospheres. And I have to multiply this times my pressure in atmospheres, 5.0 atms. And I'm not going to plug this in the calculator because I've already pre-solved it, but you can check my work. We would get 0.16 moles per liter is my concentration of the gas before I open the bottle. Once I open the bottle, obviously it's going to sit for a little bit. Bubbles are going to come out of solution, and I would expect that my concentration would decrease. So sure enough, let's check. 0.031 moles over liter atmospheres times 4.0 times 10 to the negative 4th atm, and I would end up getting 1.2 times 10 to the negative 5th moles per liter. Okay, so the concentration does go down significantly as a result of opening the bottle, which makes sense. All right. There are 3 different ways to qualitatively describe our solutions. We have unsaturated, saturated, and supersaturated. You may or may not have done a POGIL in honors that discussed these things. Unsaturated, that means things can still dissolve. Saturated means you are at your limit. You cannot dissolve any more particles than what you already have dissolved. And supersaturated is typically when we heat a saturated solution and then we are able to dissolve more solvent than normal. When it cools back down, those particles remain dissolved, and it is referred to as a supersaturated solution. Okay. We also have 4 ways we can calculate concentration. Molarity, you should already know. It's moles over liter. Molality, you may have seen before when talking about colligative properties, such as boiling point elevation and freezing point depression. We use molality in those calculations. That is moles per kilogram, but specifically moles of solute over kilograms of solvent. So that's something you have to be careful of. Again, molarity is moles per liter. Percent composition, so that's the grams in relationship to the volume. Sometimes you might hear mass percent. Mass percent would be the grams of your substance over grams total. All right. And then a mole fraction, which is also similar to mass percent, but it's a mole of substance over moles total. Okay, so let's calculate some. A solution is prepared by mixing 1 gram of ethanol with 100 grams of water to give a final volume of 101 milliliters. They want you to calculate pretty much everything. So let's do it. We know that in order to find molarity, I will need my moles. So I've got 1 gram of ethanol, and should convert that to moles. Again, I've pre-calculated a lot of these things to save time. 46.08 is grams is the amount of grams per mole. It's the molar mass. We end up getting 0.0217 moles, and we need to divide it by the total volume. So the total volume of our solution is 101 milliliters, which is the same as 0.101 liters. When I calculate that, I end up getting a concentration of 0.215 molar, capital M. All right. That one's not too bad. Let's look at the mass percent. Mass percent is relatively easy. Again, the mass of what you have, so mass of ethanol, C2H5OH, divided by the total mass, which is 101 grams total, and then we multiply that by 100 because it's a percentage, right? So times 100, and we get 0.990% ethanol. Okay. Very, very tiny amount. All right, next we can do the mole fraction. Well, we already have the moles of ethanol from up top. We are going to need the moles of water. There are 100 grams of water, and there are 18.02 grams for every 1 mole, which leaves me with 5.55 moles of water here. Okay. So for my mole fraction, I'm going to need the moles of ethanol, so 0.0217 moles, divided by 5.55 moles plus 0.0217 moles. Okay. And I'll get a percentage of it's not even a percentage of decimal, 0.0389 would be my mole fraction there. All right, last but not least, molality. So molality, again, it's your moles of solute over your kilograms of solvent. Well, if you remember, there were 100 grams of water, which is the same as 0.100 kilograms, right? So 100 grams is 0.1 kilograms. And we get 0.217. And we're going to use little m for molality. Capital M is molarity. Little m is molality. Okay. And we're done. And that matches up with everything that I had here, so we're good. All right. This is a good problem. The electrolyte in automobile lead storage batteries is 3.75 molar sulfuric acid solution and has a density of 1.230 grams per ml. Calculate the mass percent and the molality of your sulfuric acid. Okie dokie. So we first need to figure out how many grams there are per liter of solution. And then we can figure out how many grams there are total. So first, we want to use that density, 1.230 grams per ml. And we know that there are 1,000 ml per liter. And we end up with 1.230 times 10 to the third grams per liter. It's a terrible 3, so let me fix that. 10 to the third grams per liter. That is our overall amount of grams for our total solution. So this is the density of the whole solution, right? We do need to know, because first we got to figure out what we're finding. We're finding mass percent. So we need to find the mass of sulfuric acid, and we also need the total mass of our solution. Well, we have the total mass of our solution, which is good, but we also need to figure out how much water there is. We want the mass percent of our sulfuric acid, but we also want to know how much water there is when we go to do molality, because we need to know the kilograms of solvent. Okay, so 3.75 moles per liter sulfuric acid times 98.0 grams per mole, and that tells me I have 368 grams of sulfuric acid. All right, in total, I still need to know the amount of water, right? So I've got 1,230 grams minus 368 grams. This is again the total mass. Total minus sulfuric, and we'll know the water, okay, which is 8 862 grams. Yes, 862 grams of water. All right. So now we can do what we need. We need the mass percent. For mass percent, we've got 368 grams over 1230 grams total, right? And we want to multiply this times 100, and we get 29.9% sulfuric acid. Still fairly concentrated, right? And then molality. So molality, we need our moles, which we know is 3.75 per liter, right? 3.75 moles per liter of our solution, divided by our kilograms of solvent, which we have 862 grams, so this is 0.862 kilograms of water. And this would give us a molality of 4.35 with a little m. And we're done. The last thing I wanted to talk about, just to summarize everything, is the energies involved in solution formation. Typically, if we think about solutions, dissolving solutes in solutions can be endothermic or exothermic. There was a lab we did first semester in AP Chemistry where we looked at the different solutes that could make the best hand warmer. That hand warmer lab is a classic AP Chem lab because we're looking at different solutes, and when they dissolve, they can either release heat or they can absorb heat. And so what we need to do is look at the solution process itself. Our first step to forming a solution, like I said, we've got solute separating into its individual parts. So we have to expand our solute, right? So solute separates and expands. That's the first step. And that would be our first energy, right? Step 1. Then step 2, we need the IMFs in the solvent to be overcome, aka the expanding of our solvent. IMFs in solvent are overcome, and we expand our solute, or solvent, sorry. Once they're expanded, now they can properly mix, and when they mix, they form their solution. Now, each of those processes has its own delta H value. If we were to add all of those up, we would get the delta H of solution, which is what you ended up calculating in that hand warmer lab all those months ago. And you were able to tell if it was exothermic, overall we had a net negative energy, which means energy is being released. If it was endothermic, our delta H was positive, and we saw that it absorbed energy, or it got cooler to us, right? And that is all for our first play posit. Have a great day.